Welcome to this introductory lecture on thermal fluids, where we will establish foundational concepts essential for understanding energy transfer and transformation in physical systems. Today, we focus on the fundamental principles governing thermodynamics, starting with the key definitions and culminating in a detailed explanation of the first law of thermodynamics. System. In thermodynamics, a system refers to the specific portion of the universe under consideration for analysis. This could be any physical entity, such as a volume of gas, a steam engine, or even a cup of coffee. The system is distinguished from its surroundings by a boundary. Boundary. The boundary is the physical or conceptual surface that separates the system from its environment. It can be tangible, like the walls of a container, or imaginary, such as an arbitrarily defined surface surrounding a gaseous cloud. Environment. Everything external to the system boundary constitutes the environment or surroundings. In many practical analyses, the environment is assumed to be large enough to remain unaffected by the processes occurring within the system. State and properties. The state of a system at any instant is characterized by a set of measurable properties. These include temperature, pressure, volume, mass, energy, entropy, density, and so on. Properties are classified as 1. Extensive properties. These types of properties are dependent on system size, for example, mass, volume, total energy. Intensive properties. These types of properties are independent of system size, for example, temperature, pressure, density, processes, and cycles. A process describes the transition of a system from one thermodynamic state to another. When a series of processes returns the system to its initial state, it forms a cycle, a concept critical in the operation of engines and refrigerators. How energy is stored and transferred. Systems may store energy in various forms, including kinetic, potential, internal, chemical, nuclear, and electromagnetic energy, all quantified in joules-J. Systems are classified based on how they interact with their surroundings. An isolated system exchanges neither mass nor energy. Example of an isolated system. Thermos flask. A well-insulated thermos flask is a good practical approximation of an isolated system. The thermos prevents heat from entering or leaving the container, and no mass, like liquid or gas, can escape, making it an isolated system for all practical purposes. While it's not truly perfect, its boundary is designed to minimize the exchange of both energy and mass. A closed system exchanges energy but not mass. Examples of a closed systems. 1. Pressure cooker. A pressure cooker is a closed system because it can exchange heat, energy, with its surroundings, but the mass of the food and water inside remains fixed. Heat can flow into the cooker, making the food cook faster, but no mass can escape, apart from a little steam escaping through the safety valve, which is designed to maintain the closed boundary under normal circumstances. 2. Battery. A battery is another example of a closed system. It can exchange energy with the surroundings in the form of electrical energy, output as power to a device, but the battery's internal mass does not change, as no material is exchanged with the environment. An open system exchanges both mass and energy. Examples of open systems. 1. Boiling kettle. A boiling kettle is a classic example of an open system. It exchanges heat energy with its surroundings, from the burner to the water, and it also exchanges mass. Water vapor, steam, leaves the kettle while the liquid water stays inside. 2. Human body. The human body is an open system. We take in energy in the form of food and oxygen, and we release energy as heat and work, movement, etc. Additionally, we exchange mass with our environment by breathing in oxygen and expelling carbon dioxide, as well as through sweating, urination, and other biological processes. 3. Car engine. A car engine is another example of an open system. It takes in fuel, mass, and air, mass, burns the fuel to produce energy in the form of heat and work, and expels exhaust gases, mass. The energy from the combustion is transferred as heat and mechanical work to move the vehicle. Energy can cross the system boundary in two main ways. Heat transfer, HU. This is energy transferred because of a temperature difference. Heat entering the system is positive, leaving the system is negative. Work transfer, W. This is energy transfer by mechanical means such as force acting over a distance. Work done by the system on its surroundings is positive. Work done on the system is negative. The first law of thermodynamics. Now, with this foundation, we arrive at the first law of thermodynamics. This law expresses the fundamental principle of energy conservation as applied to thermodynamic systems. Change in U equals Q subtract W. Here, change in U represents the change in the system's internal energy. Q is the heat added to the system, and W is the work done by the system on its surroundings. Put simply, add heat in, subtract the work done out. What remains is the energy stored inside the system as internal energy. Breaking down the first law. Internal energy, U, is the microscopic energy stored within the system, including molecular motion and interactions. It depends only on the system's current state, not the path taken to reach that state. When heat is added, Q greater than zero, the system gains energy either by increasing its internal energy or by performing work. When the system performs work, W greater than zero, for instance, by expanding and pushing a piston, energy leaves the system. Thus, the change in internal energy reflects the net effect of these energy transfers. A practical example. First up, we have a container filled with water and steam. There's a flame heating it from below, but notice something important. This container has no moving parts. It's rigid. That means the volume can't change. This setup is a closed system. Mass stays inside, but heat can enter. Because the flame is heating it, heat transfer is positive. Energy flows into the system. But there's no piston or any moving boundary, so the system doesn't do any mechanical work on the surroundings. That means work transfer is zero. Now let's look at the second setup. Here we have a similar mix of water and steam, but this time it's inside a cylinder with a movable piston. The flame again adds heat, so Q is still greater than zero. But unlike before, this system can expand, pushing the piston up. This expansion means the system is doing work on its surroundings. So now, both Q and W are greater than zero. Third, the solar panel with a photovoltaic cell. This is a closed system. No mass enters or leaves. It absorbs heat from the sun, so the heat transfer is positive, and it produces electricity, meaning positive work output. Therefore, Q greater than zero and W greater than zero. Next, the space heater. If we're just talking about the heating element, no air exchange, then it's a closed system. It receives electrical work, which means work is done on it, and it releases heat, so the heat transfer is negative. Therefore, Q less than zero and W less than zero. But if air is moving in and out, then it becomes an open system because mass is crossing the boundary. 5. The internal combustion engine. This one's clearly open. Fuel and air go in, exhaust comes out. It loses heat to the environment, Q less than zero. Some of the chemical energy is lost as waste heat, but produces mechanical work, W greater than zero, rotational output on the shaft or crank. 6. The hydro turbine. Water flows in and out, so again, it's an open system. There's no significant heat exchange, but mechanical work is produced. The turbine extracts mechanical energy from the flowing water, so W greater than zero. 7. Hot block and cold water. Let's talk about a classic thermodynamics experiment. You drop a hot metal block into a container of cold water. What happens next? Let's start by looking at just the block. The block doesn't melt or break apart, and nothing enters or leaves it, so it's a closed system. This system type is closed. Q less than zero, which means losing heat, and W equals zero, which means no work is done. Since the block is hot, it loses heat to the water. That makes the heat transfer negative. We call that Q less than zero. And is the block doing any mechanical work? Nope, it's just sitting there. So the work transfer is zero. Part B. Cold water only. Now let's look at the water. Just like the block, no mass enters or leaves the water, so it's also a closed system. This system type is closed. Q greater than zero, which means the system is gaining heat. W equals zero, which means no work done. As the block transfers heat, the water gets warmer. That means it's gaining energy, so the heat transfer here is positive. Q greater than 0. And again, no work is being done. The water's not moving any machinery or lifting anything. So, W equals 0. Both the block and the water individually are closed systems, assuming no evaporation. Part C. Combined system. Block plus water in a closed container. System type. Isolated. If the container is perfectly insulated, no heat, work, or mass is exchanged with the outside. No heat enters or exits. Heat just redistributes inside. Therefore, Q equals 0. Work transfer equals 0. In summary, all energy changes happen internally, so this is a classic isolated system. Important points to remember. 1. The first law is essentially an energy balance. Energy entering minus energy leaving equals the change in stored energy. 2. It applies to any thermodynamic system, gases, liquids, solids, or even chemical reactions. 3. Energy forms include heat, mechanical work, electrical energy, and chemical energy. Understanding the first law of thermodynamics unlocks the secrets of energy transformation and equips us to design efficient machines and sustainable energy systems. Thank you so much for watching. If you found this video helpful, please don't forget to like, share, and subscribe to our channel. Your support really helps us create more quality content like this. We'd also love to hear from you. Please drop a comment below and tell us where you're watching from. Whether you're tuning in from a city nearby or somewhere across the globe, we want to connect with you. Your feedback and questions are always welcome, so feel free to engage with us. Thanks again for being part of our learning community. See you in the next video.